Hello everyone. The title of this video is Euler's Method, and of course I'm going to be going over several examples where we use Euler's method to approximate the value of a solution curve, a function that solves a differential equation given a certain initial condition. Euler's method is used to approximate a solution, the value of a solution curve at a given input. And of course, this approximation can be either very good or very poor, depending on the different scenarios you're in. Alright, so what I'm going to do in this video is first go over what Euler's method is. Then I'm going to go over I've got three examples. We'll get to 2 or 3 depending on how long it takes me. And in some of the examples, I'll show you how to approximate a certain value of a solution curve at a given input using Euler's method, and then we'll compare that value, that approximation, to the actual value based on the actual solution curve that you should know how to find. Like I said, we'll get into all that in a few minutes here. Alright, so I'm getting started here with a discussion of, what is this thing called Euler's method. So we have an initial value problem. Y prime, or dy dx, equals some function f of x and y. So y is the dependent variable, x is the independent variable. And we're given an initial condition. Alright, the value of this function y at x equals, say, x sub 0 is some value y sub 0. Alright, so suppose there is a solution curve, a solution, y of x that passes through this point x sub 0 comma y sub 0, which I have labeled here in red. Now suppose I wished to figure out what's the value of the solution curve at, say, x equals x sub I'll say x sub k or whatever. Alright, so here's the actual value. Alright, and then we'll call this y sub k here. So here's the actual value on the solution curve at this x sub k. But what if we didn't know the solution curve? What if this were some sort of equation, maybe like some crazy non-linear equation that you didn't know how to solve, right? So you couldn't find an exact expression for the solution curve. So what do we do in that case? How do we find this value of the solution, if it exists, at x1 if we don't know the solution curve? Well, we can use tangent lines, right? Remember y prime, the first derivative of y with respect to x? Remember, this was the slope of the tangent line at any point, right? So just recall that this is going back to first year calculus, Calc 1. Y prime is the slope of a tangent line. Right. Remember, you used that fact to make direction fields or slope fields before. Well, we're going to use that fact to help us here now. So if I want to get up here eventually, right, this point, to approximate the value at this point, I take the tangent line at the point that I'm given, the initial condition. Right, there's the tangent line. And the slope right, the slope of this tangent line is y prime, but y prime is just the value of this function here at whatever is a point on the curve. So it would be f of x sub 0, y sub 0, right? The point x sub 0, y sub 0 is on this line. I'm doing the tangent line at that point, and that is what is given to us as y prime, right? The slope. And the equation of this tangent line would be the following. Would be y equals, y sub 0, right, the y value that you're at, plus the slope, right, f of x sub 0, y sub 0. That's the slope times the change in x minus x sub 0. Right. And what we're going to do is we're going to use this and kind of make little steps. Right. Make little steps along the tangent line to help us get toward the point in question, to get as close to this point as we can. So the little steps we take are steps of h units, right? And the book I'm looking at, a lot of books, you make a step of h units. So say I start at x0. I start with at the point x0, y0. And I want to eventually get over to this x sub k here. So first I make a step x sub 0 plus h, which I'll call x sub 1. Alright, so x sub 1 is x sub 0 plus h. So we're going to have these steps. We're going to have these steps of h units. Alright, and let's see where that takes me. So I'm traveling from here, moving along this tangent line to here. And then here's the point x1, comma, and then we'll call the y value of that y1. Right. And what I would like to figure out is, what is this y1? Right. Well, if it's on this line, we just plug things in. Right. So y1, right, y1 is y0 plus x1 minus x0 times f at x0, y0, right, times the slope of that line. And this x1 minus x0, that's the length of this step, right? x1 minus x0, that's the h units step that I'm taking to the right here, or to the left if h were negative. This is just h. So what I'm seeing here is that the value of this y1 is equal to the value y0 that I started at, plus h, right, the length of my step, my change in horizontal position, times f of x0, y0. Right. And then you start over, right? What we're going to do now, instead of being at x0, y0, now I'm going to be at x1, y1, and continue stepping toward xk. Now x1, y1, there's going to be another line with this y prime at f of x1, y1 will give me the slope of some other line, right? It's almost as if you're traveling along a direction field, right? You're traveling through a slope field from one point to another point. Then you take the slope at that point, travel to another point, take the slope at that point, travel to another point, until we get to x sub k here. So I'm just going to do this one more time, as the drawing is going to get a little cluttered. But then at x1, y1, there's another slope in the slope field, and another line, right? Another line with a slope of f at x1, y1, right? And then what I'm doing again is I'm taking this step of h units, right? I take another step of h units, and that takes me to what I'm going to call x2, which is just x0 plus 2h, or x1 plus 1h. and then x2 is the input. I go to the line, whatever that output is, that's y2. And here's the point x2, y2. Sorry about the clutteredness of this. And then my question is, what's y2? Well, the equation of this line, sorry, one more little arrow here, would just be y minus y1, or y equals y1 plus, and then the slope f of x1, y1 times, and then x minus x1. Well, if I want to know the value of y2, I just plug things in. y2 for y here equals y1 plus, and then x2 minus x1 times f of x1, y1, right, times the slope. And again, x2 minus x1 is the length of this rightward step, this horizontal step h. So we see that y2 equals y1 plus h times f of x1, y1. And hopefully you see a pattern going on here. Look at how I got y1 involving x0, y0. And look at how I got y2. It's the same form basically. And then I would just keep doing this. Now that I'm at x2, y2, what's the slope determined by the differential equation? If I was making slope, traveling along a slope field, make a line, and then travel h units to the right to x3, y3, then x4, y4, all the way to this xk, yk. But we're seeing that the form that we're getting, to find y1, y2, y3, y4, it looks exactly the same every single time. So I could keep this procedure going, and we eventually get that y sub n plus 1. Right, then I'll just say the next one down. Y sub n plus 1 equals y sub n, right, the previous output, plus this h step that we're taking, this h for the horizontal movement left or right, what's that step I'm taking every single time, multiplied by f at x sub n, y sub n. Right? So this is Euler's formula here for Euler's method, the recursive formula for Euler's method. Euler's method. And again, hopefully this made, the drawing got a little cluttered. And then you can see that these points too on these lines with the slopes that are coming from the differential equation, they're off of the solution curve, right? There should be a little bit of error, unless the solution curve were a straight line. Euler's method is always going to be a little off of the actual solution, which we'll see in our first example. All right, so I'm going to keep this up here, right? This recursive formula for Euler's method, and show you what the heck's going on here. All right. So in my first example, and all the examples I have in this video, I am asked to use Euler's method to obtain a 4-decimal approximation of the indicated value. Alright, so we're given our initial value problem here, right, IVP. So y prime equals 2 times x minus 3 times y plus 1. This is that f of xy that was mentioned on the previous pages. Right? So I've got a description of the slope of the line tangent to the curve, any solution curve going through the point xy, right? Any point xy in the plane. And we're given an initial condition, the value of the function y, that is whatever the solution curve to this is, the value of y at x equals 1 is 5. All right, so this means we're starting at the point 1, 5, and then this 1 I'll call, that's my x sub 0, and this 5 is y sub 0. Right. And what we're asked to do is, knowing this, approximate, this equation has some sort of solution curve that, that satisfies it and passes through the point 1,5. We're asked to approximate the value of this solution at x equals 1.2 to 4 decimal places using Euler's method. Now, how good the approximation is going to be depends on the value of this h. I remember I was stepping to the right or to the left, if h is negative, h units. So first I'm going to do it when h is just simply 0.1. Right? So h equals 0.1. Right. So again, if that's the case, we know when x0 equals 1, y0 equals 5, and then I make a jump, right? I make a step of h, right? I have, again, h equals 0.1. I make a step to the right 1.1 units. We get x1 equals 1.1, right? And then we need to find y1 using our recursive formula, right? So y1, using this formula up here, right, y1 would just be y0 plus h, so 0.1, right, h is 0.1 times, and then f of xn, yn, f of x0, y0. So 2 times x, again, so 2 times x0 minus 3 times y0 plus 1, right? There's, in the brackets here, this is the f of x0, y0, and that's how we're going to find our next y value, y1. And this is going to be what y is approximately 1.1. Right, and then we just got to take one more step to get the value of y approximated at x equals 1.2. Alright, so y sub 0 we said was 5, right, plus, and then 0.1 times 2 times 1 minus 3 times 5 plus 1. This is 2 minus 15. 2 minus 15, right, so negative 13 plus 1, negative 12, but a tenth of that's minus 1.2, so y sub 1 is 3.8, right, 3.8. So this is approximately, again, the value of our solution at 1.1, right, at x1. Notice I put approximately, right. Okay, and then to get the approximate value of y at 1.2, using this step size of 0.1, I just need to take one more step. Right? So again, h equals 0.1, and then we're getting x2. Right, so I took 2 steps here to get from 1 to 1.2 with these step sizes of 0.1, equals 1.2, and then this is where I'm going to end it, right? Because I'm at 1.2, and I'm at this input of 1.2. And using our recursion formula, right, y2, which is the approximation we're looking for, would be equal to y1 plus h, right, 0.1, times, and then f of x1, y1. So 2 times x1, so 2 times 1.1, minus 3 times y1. Y1 we saw from earlier was 3.8. And then plus 1, right? And then again, we can do this by hand. Now y1 was again 3.8, right? So this is 3.8. Now this is 2.2, right? This is 2.2, 2 times 1.1. 3 times 3.8, 3 times 3 is 9. 3 times 0.8 would be 2.4. This is minus 11.4. Now 2.2 minus 11.4 is negative 9.2, and then plus 1 would be negative 8.2. All right, so this here, just kind of flash the calculator. Showed you how I'm using the calculator, man. This is negative 8.2, and then 1/10 of that is negative 0.082. So we subtract that from 3.8. 3.8 minus 0.082. I'm sorry, just 0.82. 3.8 minus 0.82. And we're getting about 2.98. Right, we're getting 2.98. So y2 equals 2.98. And this is the and I guess you could go 0, 0 here, right? 2.9800, because they did ask for an approximation to 4 decimal places. So this is approximately the value of y at 1.2. And there we go. Okay. Now that's using a step of h equals 0.1, where I started at x0 equals 1, and then I just kept moving to the right by 0.1 units until I got to x equals 1.2 and get my approximation. All right. Now, yes, this is all done by hand. Wonderful. I would recommend, though, because I mean, yeah, there was only 2 steps here, but the next part I'm going to show you is going to involve more steps, and I could go more steps, and the more steps, obviously, the more annoying this gets. I mean, writing all this out took a while. What I want to show you is a calculator. All right, I have a TI-84 Plus here. And there it is, should be on your screen now. You see the main screen here, and then all the buttons on the left. So what I like to do, if you're using a TI-84, and I'll show you in an alternate way as well, you can go to a website. You can go to some website with a numerical solver to make this real fast. But so I like to start with y sub 0. Just enter the y sub 0 was 5, right? Y of 1 was 5. Y sub 0 was 5. So I hit enter, hit 5, hit enter. All right. Then I enter my recursion formula. All right, where that was up here. I'm dragging this down. Hopefully you can see this still. All right. Oh, slide it back up. There we go. Where I'm going to enter this expression over here. The y sub n plus h times f of x sub n y sub n. I'm going to enter this in my calculator, but in the following way. Y sub 1 would be y sub 0, which was 5. So I just go second answer. All right, I take the previous answer, that's the y sub n, plus h here is 0.1 times, and then in parentheses, f of x sub n, y sub n. Now f of xy was this 2x minus 3y plus 1. So I go 2 times, and then x sub n. Well, x sub 0 in this case, right? Because we're finding y1. X sub 0 is 1, but since I'm going to be adding 0.1 every time, I'm going to do that in 2 decimal places. 1.0. There's x sub 0, 1.0. Minus 3 times y sub 0, which is again the previous answer. So I just do y sub 0, the previous answer of 5. And you'll see why I'm doing this whole previous answer thing and all that when this comes up. And then plus 1, right? plus 1, and then close parentheses. So there's the, y sub n plus h times, and then f of x sub n minus, y sub n, 2 times x sub n minus 3 times y sub n plus 1. All right, and I'll hit enter on this, and you see 3.8. Remember how that was my y sub 1? So I'll drag my paper over here. All right, remember how I'm on the bottom here. You see remember how that was my y sub 1, 3.8? This approximated the value of the solution at 1.1. Right? And then to have this just re-enter, what I'm going to do is I'm going to hit the second button, and then above the enter button it says entry. It enters the previous answer, but now when you see ANS, right? When you see ANS, it means 3.8 instead of 5. Right? So that's what's going on, right? That previous y value is being used, and then all I need to do is move my cursor through to change the previous x values from 1.0 to 1.1. Right? That's why I made it 1.0 earlier. And now this should give me the approximation at x equals 1.2. This should give me an approximation of y at x equals 1.2. I hit enter, and look, 2.98, which is exactly what I ended up with when I was doing it by hand. Y2 equals 2.98, and that's our approximation of y at 1.2. Okay. All right, so let me do that again. Let's get rid of the calculator for now. And I want to show you another way you can do this. Another place you can find a way to approximate a solution using Euler's method. It's through what's called a numerical solver. So I'm going to pull up some websites here. So I'm on Google. All I typed in was Euler's method numerical solver. And I'll go to the very first one here, Euler's method calculator. All right. Now up pops, y prime equals, and then you just have to put in some function. Now they're using t and y instead of x and y, so just replace all the x's with t's. All right. So this expression here, instead of t times y, I type in, what was it? It was 2 times x minus 3 times y plus 1. So 2 times t minus 3 times y plus 1. All right. And then the value of h, right, that step size was 0.1. T sub 0 was 1.0 or just 1, right? That was our initial x value or initial t value here. Y sub 0, right, the initial y value was 5. And then where do we want to go? What's the last x value we want to be at? We want to be at 1.2. Remember, I want the approximation of the solution at x equals 1.2, or in this case, t equals 1.2. Then I hit enter after I've entered all this, and then it shows you below this all the steps. All right, look at this. All the eventually it comes up. All these dollar signs here. Okay, you see y at 11. Now it's using fractions, but y at 1.1 is a 3.8, approximately 3.8. That's what we got after our first step. Then y at 1.2, which is 6/5, is approximately 2.98, which is what we got after our second step. And it shows you all the calculations they did, right? Step 1, step 2, the stuff I wrote out by hand, right? Just like the stuff I wrote out by hand. All right. So this is a beautiful thing right here. This is, again, just replace x with t, and you'll be fine. Okay. All right, so now what I want to do, all right, I'll keep that up. I'll keep the that numerical solver up. But now what I want to do is do this also with, that was when h was equal to 0.1. We ended up with this being approximately 2.98. Again, this was with h equal to 0.1. And what you'll find is that the finer you make your steps, right, the smaller you make this value of h, the better the approximation should get to the actual value. And we'll get to what the actual value of y at 1.2 is. We'll get to that in a minute. All right. So now what I want to do is, with h equal to 0.05, so instead of 1/10, we'll go 5/100ths or 1/20th. Right? So part 2, with h equal to 0.05. Right. So again, x sub 0 is 1, y sub 0 is 5. And then I make my step of h, and we get x1 equals 1.05, right? I'm going from 1 to 1.05 now. And y sub 1, using our recursion formula, would be y sub 0, so 5, plus h, 0.05, times f at x sub 0, y sub 0. So f at x, 2 times x sub 0 minus 3 times y sub 0 plus 1. And we get, some sort of approximation here. Again, this is 2 minus 15. This is negative 12. 12 times 5 is 60. And so negative 12 times 5/100ths. That would be negative 60/100ths, or negative 0.6. So 5 minus 0.6, 4.4. And that's our approximation of y at 1.05. All right. And you see how I'd have to take, instead of just 2 steps, we're trying to get to 1.2 here. I'll be taking 4 steps, right? Because if I go h again, I get x2 equals 1.05 plus 0.05 again would be 1.1, or 1.10 if you want to call it that. And then y2, our approximation at 1.1, is going to be the previous, y1, 4.4, plus h, 0.05, times, and then the value of the function, the value of the slope at x1, y1. All right, so 2 times x1, which was 1.05, minus 3 times y1, which was the 4.4, plus 1. All right, and we get another y2, which is again the approximation of our solution at 1.1. And I'll do this on the calculator. All right, I'll do this on the calculator. So let me pull that calculator up again, and I'll also show you on the numerical solver. All right, so let's clear all this. So again, I'm going to start with y0, 5, enter. And then I take that previous answer plus h, right, 0.05 times, and then in parentheses, f of x, the previous x, the previous y. So 2 times, now since I'm going to be adding 0.05 every time, I'm going to go 2 decimal places on this. I'm going to go 2 times, x0 is 1.00, minus 3 times y sub 0 was, again, the previous answer. When I see y sub n, I'll just put in the previous answer, plus 1. All right, and enter. All right, you see the 4.4, right? Exactly like I got when I wrote it out, right? Y sub 1 equals 4.4. So that's at 1.05. Then the next step, when x equals 1.1, and I just go second entry, and then just change my previous x from 1.00 to 1.05. All right, so moving the cursor there change that to 1.05, and you see 3.895. That's the approximation of y. 3.895. That's the approximation of the solution at 1.1. And then we'll get y at 1.15 approximated. Right, next, so I'm going to go second entry, and then change the previous x from 1.05 to 1.15, getting 3.47575. And then finally, one more step, I'll get the approximation of y at 1.2, right, which is what we were asked for. So again, second entry, and change my previous x 1.15 to 1.20. Oh no. No. Okay. I made a mistake there. I apologize. Probably caught that. My previous x here was 1.05, and I added 0.1. I didn't add 0.05. So let me change. Sorry about that. That should be 1.10. So let me change that to 1. Eep. Alright, I gotta technically start this over then. I am so sorry because of all the answers. So, sorry. One more time. So, enter 5, right, and then previous answer plus h.05 times, see, one little mistake can throw everything off, right? Then 2 times 1.00 minus 3 times previous answer plus 1. Great, the 4.4, re-enter that, change 1.00 to 1.05, re-enter that. Alright, then I'm going to change, this is where I made the mistake last time, I apologize again, 1.05 to 1.10, not 1.15, 1.10. There, alright, so this should be 3.47075 for the approximation of y at 1.15. Alright, then I'll change 1.10 to 1.15 in this calculation and get my approximation of y at 1.2. Alright, so now I go through and change 1.10 to 1.15, and here we go. So our approximation is, to 4 decimal places, 3.1151. There you go. Alright, 3.1151. Our approximation of y, the solution to this differential equation, this initial value problem, at 1.2. Alright, now again, you can also, let me get rid of the calculator here, go to that numerical solver, right, pull up the website again, and same, again, t is replacing x here. Same thing, all I need to do is change h from 0.1 to 0.05. I hit enter, and then all these calculations, these 4 steps I went through on the calculator there, are put in down here, and it goes through, see, step 1, 2, 3, and 4, and look at that. Well, it eventually comes up. Basically, the final approximation, 3.1151, exactly what I wrote down a second ago. Right? It eventually all clears up nicely, right? See, so y at 1.2 6/5 is approximately 3.1151. All right, just as I did. I didn't write out all the steps by hand. I might ask you to if I test you on it. But yeah. Alright, so now one last thing I wanted to do for this example, and then the next 2 examples will be much faster because I'm not going to write out everything by hand. I'm just going to show you, the calculations in the calculator and through this numerical solver, and you decide which one you like better. Me personally, I like just going to some numerical solver page like this, and this one especially. I mean, it just it has everything written out for you, nice and neat. Alright, so getting rid of the sites here. Alright. So we had the approximation of y. The solution to this initial value problem at 1.2 is approximately 2.98 when h was 0.1, approximately 3.1151 right, when h was 0.05, and this would change, as h gets smaller and smaller. But let's find the exact value. All right, let's find the exact value of y at 1.22. Now, I'm hoping you know how to. This is a linear first-order non-homogeneous equation, and I'm hoping that you know how to solve this. All right, and I'm assuming you do. I've gone over videos in the past where we solve linear non-homogeneous equations, and here is the solution. This curve. All right, this is the exact solution curve to this initial value problem. Y equals 38/9 times e to the negative 3x plus 3 power plus 2/3 x plus 1/9. And again, I'm hoping you should know how to do this. So the exact value that we're looking for, the value of y, our solution curve at 1.2 equals, and I'll just again enter this, just replace all the x's with 1.2, and I'll put them what I get on my calculator. All right, so this number just popped up on your screen here. This is entering 1.2 in for x here and here. And then so the exact value of the solution to this initial value problem at x equals 1.2 is 3.22831579. See how I was getting a little more accurate with Euler's method as h got smaller? Now you could make h even smaller. Now this is 1/10th, 1/20th. You could make it 100th, 1000th, and go. But that would just increase the number of steps, and writing it out by hand would be a little tedious. But you should see that the smaller h gets, the closer this value approximation should get to this 3.2283 number. And it was kind of doing that, right? When h was 1/10th, our approximate value using Euler's method was 2.98. When h was 1/20th, or 500ths, our approximate value for y at 1.2 using Euler's method is 3.11. It's getting closer, to this exact value of 3.22. Okay. So just please know that, right? The smaller h is, and if things are in a convenient setup, there are some functions where maybe it'll get less accurate, but I'm not going to get into all that when that happens. But for the most part, the exercises you're going to be seeing, when h gets smaller, the approximate value you get from Euler's method should get closer and closer to the exact value. The error should be getting smaller and smaller. Okay, so yes, I know I'm almost 44 minutes in here, but that was one example. The next examples should go by a little more quickly, because again, I'm not really going to write out every single little step. Okay, so let's do that again. So again, I'll keep the recursive formula up. Right, there was this recursive formula for Euler's method. All right, now my next example is one where I can't really figure out. I mean, using methods that I've shown in previous videos, can't really go about solving this exactly just yet. All right, might see some methods in the future, but for right now, this is a non-linear, because of the y squared. This is a non-linear first-order differential equation. So all the methods I've gone over in previous videos have been for solving linear differential equations. So yeah. Now you might be able to say, hey, this might be an exact equation or whatever, all right? But I'm not going to get into all that. So this one I'm not going to find the exact solution, and you don't have to. All right, you don't have to. What we're asked to do is simply approximate approximate the value of the solution, whatever solution curve this initial value problem has, we're asked to approximate the value of that solution curve at x equals 0.2. All right, so here, x sub 0 is 0, y sub 0 is 0. All right. And then just as before, part 1, I'll have our h just be just 1/10, right? Just 1/10. Right. So if I do that, it should only take 2 steps, right? I'd go from 0 to 0.1, and then from 0.1 to 0.2, right? There should only be 2 steps. So again, x0 equals 0, y sub 0 equals 0. Then x sub 1 would be, just adding h here, right? 0.1. And then using the recursive formula, y sub 1 would be y sub 0 plus h times f of x sub 0, y sub 0. So y sub 0 was, 0 plus h is 0.1 times, and then f of x sub 0, y sub 0 would be 0 plus 0 squared. Right. Okay, so this doesn't give us too much interesting stuff here. So y sub 1 is also 0. But then it's y sub 2 that will actually give me something, right? X sub 2 would be 0.2. And then y sub 2 will be y sub 1, which is 0, plus h, 0.1, times, and then, x sub 1 squared, so 0.1 plus y sub 1 squared, so plus 0 squared. And we're just getting 0.1 times 0.1, which is 0.01, right? So all I'm getting for the approximation here of y at 0.2 is 0.01. Right? But again, I could have easily done this on a calculator. And let me pull that up again. Calculator pulled up, clear this out. Y sub 0 was 0, so I start with that. And then the next one will be the previous y, so answer plus h 0.1 times, and then f of the previous x plus the previous y. Well, the previous x was 0.0 plus the previous y squared, and then again previous answer squared. Close that off. So there's that, and then I hit entry, second entry, change 0.0 to 0.1, and we're getting what I said. We're getting the y at 0.2 is approximately. I'll just put it up here. Approximately 0.01. Now this is again when the steps I'm taking are only 1/10 of a unit long. But when h equals, let's do this down here, when h equals 0.05 or 0.01 or whatever you want, right? It's just in the book I'm looking at, they just use these two right off the bat, and then again you can make it more and more accurate if you wish by making h smaller. So again, there'd be 4 steps, right? x0 would be 0, x1 would be 0.05, x2 would be 0.10, x3 would be 0.15, and then x4 would be 0.2, right? So 1, 2, 3, 4 steps, just like earlier, right? Because it just just cuts this in half, right? 1/10 to 1/20, that's half. So you double the steps that you take. And I'm just going to go straight to the I'm going to go straight to that numerical solver. All right. So going back up here, this time again the expression is x plus y squared for y prime, right? So t plus y squared, and it's y raised to the second like that with the caret. H 0.05, I said. We're starting at x0 equals 0. Right, so t0 equals 0. y0 was 0. And we want to end at t equals 0.2. Right, so hit enter. Again, it's going to take a little while to do all that stuff here. There should be 4 steps. Right? They got the 4 steps there. And you see it's approximately 0.0150. Right, 0.0150 after all that. All right, so I'll just go back up. Let's take this off. That'll come up clean eventually. But this is approximately 0.0150, when h equals 0.05. And again, the smaller h gets, the more and more refined the approximation will get. Hopefully, the less error from the actual answer you will have. All right, and I just got one more. All right, again, if you'd write out the 4 steps if I asked you to do it by hand, but I'm not. Like I said, I don't really feel like doing it for purposes of time. But if I were asked you to do it by hand, right, you would write out the 4 steps like I wrote out the 2 steps here. All right, we got just one final example. Now, the first example you could solve. The second example you couldn't. It was a nonlinear first order equation. And here's one final example that you can solve. Again, now this one's a very easy one. I think I saved the easiest one for last. I'll just tell you right now, right? The y prime equals y, and y of 0 equals 1. The solution of this equation, the solution of this initial value problem is y equals e to the x. And I'm asked to approximate y of 1. Now the exact answer would simply just be y of 1 equals e, right, which is equal to 2.7182818459045, right? So there's the exact answer. But again, using Euler's method, let's approximate this. So again, I'll just have h equals 0.1, y of 1 is approximately, h equals 0.05, y of 1 is approximately, and heck, let's go a little further. H equals 0.01, right? Instead of 500ths, let's go 100th, something even smaller. Y of 1 is approximately, right? I'm just going to go to that numerical solver and just have y prime equal to y here and y of 0 equal to 1. So pulling this back up, going back up here. So yeah, just y prime equals y. H equals I'll start with 0.1. X of 0 is 0. T0 is 0. That's x0. Y0 is 1, right? The initial y value. And we're going up to 1.0, or just 1 here. Now, notice that would take 10 steps, right? Because if you go from 0 to 1 and you're only increasing by 1/10 every time, that'd be 10 steps, which you could do by hand, but it'd be kind of annoying. Especially when we use h equals 0.05, that'd be 20 steps, and h equals 0.01, that'd be 100 steps. Right, so I would rather not write that stuff out by hand. All right, so when h equals, say, there should be 10 steps here. I don't even know if it's going to do the other ones. We'll see. So y1 is approximately 2.5937. If I go to 4 decimal places, 2.5937. Right. All right, and if I change, h from 0.1 to 0.05, it'll increase it to 20 steps. Step 1. So maybe I won't do the. All right. So let's see if it works out. So when h equals 0.05, the value of y at 1 is approximately 2.6533 if I round to 4 decimal places. And you see how that's getting closer to e, right? The actual value at 1 for the solution to this initial value problem would be e, 2.7182818. This is getting closer. All right, I'll try one more time. Let's go hit home here. Let's go back up here and change h to 0.01 and see if it actually hit enter and see if it actually brings up 100 steps, because it would be 100 steps. Yeah, looks like it does. Wow. Yeah, this is pretty nice. Now, obviously, I would never ask you to write something like this out by hand with 100 steps. Maybe the 4 steps, 5 steps, but not 100. And look at that. Y of 1 is approximately 2.7048. If I go to 4 decimal places, round to 4 decimal places. All right, so getting rid of this. All right, so look at this, right? Now again, the exact value we know is E, 2.718. And you see how this gets closer and closer and closer. It's getting closer to the exact value E as the value of H shrinks down. Now, it's not very good, right? And I'll tell you right now, Euler's method isn't the greatest at approximating solutions. It's all right. It's pretty nice. It's a good start. But what we're going to see in future videos, I got a couple more to make here. We'll see something called the improved Euler's method that gets towards the exact answer more quickly than this regular Euler's method. And then we're going to see what are called the Runge-Kutta or Runge-Kutta methods, depending on how you pronounce it. And specifically a Runge-Kutta method of fourth order, sometimes referred to as RK4. And that's much more accurate than this basic Euler's method and approximates your solutions much more quickly, much more accurately. But that's, for future videos. All right. So again, hopefully you got this down, right? This is the most important thing here. If you're asked to do this by hand, what the recursion formula is, how do I get from one set of x values and y values to the next guess, right? For the next x value, you just add h, right? The x sub n plus 1 is just x sub n plus h, right? You just add h. But y sub n is found this way, right? All right, it's almost an hour here, but I got 3 examples in. Hopefully watching me go over these 3 examples. That one little mistake aside, I apologize for the the misentering of a calculator problem, or one of the calculator parts. But quickly caught it though. Right? Hopefully you can catch your mistakes as quickly. But hopefully watching me go over these few examples here and going over the explanation of Euler's method. Hopefully this all helps you when you're working on some Euler's method problems on your own. And thank you very much for watching.